So I'm Buddhika, and I'm from Indiana University, and I'm going to present a work on lightweight instrumentation called instruction planning. So let's say you're debugging, performance debugging your favorite memory allocator. So you enable the profiler to see if you can find something wrong. And when you engage this profiler, what it would do is to inject a couple of probes to the function that you're profiling. In this case, the memory allocation function. So ideally, you would want this profiler not to slow down this application by too much. So whatever the probe injection mechanism this profiler is using needs to be low overhead, both when attaching the probes and also when running those probes. So we want it to be low overhead. And let's say you profile it, and then you confirmed your suspicion that this memory allocator indeed sucks. So now you want to investigate more, and so you open up the code, and you see this huge for loop, which looks really suspicious. So now you want to profile this for loop. So for that, you just need to move these probes to measure just the for loop. So that means for this kind of exploratory debugging, you need to be able to probe any arbitrary location in the application. So this little story brings us to the basic question that we're trying to answer with this work, which is, can we runtime probe an application at any instruction with low overhead? So the typical method of probing applications is by using called trampolines. So let's see how this works. So let's say we want to probe at this highlighted instruction at the instruction stream. So the first step is to generate or JIT the called trampoline, which contains the call to the actual instrumentation function. And as the next step, what you do is to relocate the probed instruction or to the trampoline, because as the final step, we are going to overwrite it with the trampoline jump, which will, at the runtime, will transfer the control to this trampoline and into the instrumentation function. So Dynins is like the state-of-the-art in runtime instrumentation like this, and it uses this trampoline-based probe injection mechanism. So the next question is this cheap? So the probe invocation is certainly not that expensive, because it just involves a double indirect jump from the mainline code to the trampoline and then to the instrumentation function. So in modern hardware, this is typically around several dozen cycles probably. How about probe injection? So the cost of probe injection depends on how cheap you can patch in this trampoline jump to the mainline code. So one obvious solution is to stop all the threads and do the patch. And this is exactly what Dynins does. But unfortunately, this is not cheap, because now every time you want to probe the application, you have to stop it, which is obviously not scalable. So in a previous work, we came up with this protocol named Wordpatch, which can be used to safely patch an instruction word of an application without stopping it. So with this protocol, the best case is just a regular memory write, but the worst case is when you want to patch an instruction which straddles a cache line boundary. So this worst case is around 8,000 cycles on several recent architectures. But it's relatively infrequent because it only happens at cache line boundaries. But it's definitely cheaper than stopping all the threads to effect this patch. So now we have a relatively cheap way to inject a probe, which is cheaply knock. So the only remaining question now is, can we probe any instruction using a trampoline jump? So this is the main contribution of our current work. And it turns out that it is tricky when the instruction is shorter than a jump instruction. So in x86, a relative jump looks like this. It's like of length 5 bytes, and the first byte is for the opcode, and rest of the 4 bytes are for the relative distance to the jump target. And going back to the malloc example, so now let's say we want to instrument the entry point to this malloc function, which is like a 3-byte instruction, which is obviously shorter than a jump. And also, let's say this second instruction is a target of a jump somewhere downstream, this malloc function. So now, if we probe here, our jump will basically override the first 2 instructions. And is this safe? So I have like zoomed in on these first 2 instructions and sort of laid them out side by side, and you can see the incoming control flow edge at the second instruction head. So let's say we override with our jump. So now you can probably see the problem here, because this incoming control flow edge now lands on somewhere inside this trampoline jump offset, which we just overrode. And this byte sequence RS may or may not be a valid instruction, and definitely not the instruction that we wanted to execute at this place. So this is sort of unsound. So one way to get around this problem would be to craft this trampoline jump offset in a way such that it contains a trap at the second instruction head. So that now when if a thread comes along and try to execute this second instruction, it would trap, basically. And inside the trap handler, we can figure out where this trap originated and reroute the control of this second thread to be inside the trampoline, where we now have relocated this second instruction into. So this is getting into the basic idea of instruction punning, where we sort of treat data as code. So data in this case is like trampoline jump offset, and it contains code in the form of single byte traps, which maintains the original instruction heads. So it seems as if we've sort of solved this problem in this particular case, but there's another case, even this fails to work. So let's see that. So let's say this first instruction is like of length 4 bytes now. And if we try to play the same trick, now this trap will end up being at the very last byte of this offset. And x86 is a little endian, so we need to reverse the byte order to get the actual offset value. And now you can see this offset starts with the hex value C at the most significant byte, which is in 2's complement a negative, and actually this is a large negative number. And if you add this offset to get the absolute address, it will most probably be a negative number. And this is bad because obviously we cannot have negative virtual memory addresses. So again, unfortunately, we're stuck. But this is not the end of the road, because in x86, 64-bit, it's got this 14 single byte illegal instructions, which can also generate signals. And more importantly, these illegal instructions do not cause negative offsets when you add this particular byte portion. So this is great news. Now we can use these illegal instructions instead of a trap if we come across this particular scenario. So this is the basic trick or the idea of instruction punning, where we use illegal instructions and our traps to figure out good trampoline offsets depending on the instruction layout at the probe site. So we call these offsets as puns because, like as I mentioned, these offsets serves a dual purpose as data and as code. And these puns should obviously result in addresses where we can actually allocate these code trampolines. So ideally, we need to limit the memory usage of these trampolines. So on one hand, we need to spread them out so that they do not collide with each other. But also, we need to try to pack them tightly as possible. So let's see how this offset selection works. So let's say we want to pick a value for these offset bytes B, C, D, and E here. So x86 is little endian again, so we need to reverse the byte order to get the offset value. And let's say a memory page is like 4 KB, which is typical. So that means the least 12 significant bits of this offset addresses intra-page memory locations when we add this offset to get the absolute address of the jump target. And the rest of the 20 bits addresses memory location at a memory page granularity. Especially these two most significant bytes can be used to like select the target memory page. So we call these two bytes a page selector for that reason. Okay, so let's see how this search works. So let's say we want to probe this move instructions, which is somewhere inside the text segment. And you can see the trampoline offset bytes that we want to fill in at this particular location on top of this move instruction. So we start off by zero initializing this offset. And then we fix this page selector to be a permutation of illegal instructions. And we do this irrespective of whether these bytes are like constrained in the original instruction layout or not. So this helps us to like restrict the search space by quite a bit. So let's say this page that it gives is unfortunately somewhere inside the heap, already allocated heap. So if we try to map here, it would obviously fail. So what we do is like keep a rough estimate of where the heap, stack, and the text is, and try to avoid, like rule out basically these kind of obvious collisions even before trying to map. Okay, so since that failed, we try another permutation for the page selector. And this time around, let's say it gives us a page which is not known to collide with any of these already occupied memory areas. And then we try to mmap this trampoline page. And given that it's successful, now we can lay out our trampoline inside this trampoline page. And we are done. So now let's say we decide okay, we want to probe the instruction which is like next to the instruction we just probed. Again, we start off in the same way. And the important thing to note here is that we try the page selectors in the same order. So we start off with the initial page selector, which again would most probably end us up inside the heap because it's only offset by several bytes. Again, we rule this out. And then we try the second page selector. And this is where the interesting thing happens because it would give us the same address, or same trampoline page address we already have allocated. So this is good. But unfortunately, there's already a trampoline occupying at the start of the this trampoline page. So now what we do is to sort of fiddle these low order bytes of this offset so that we find a placement for this trampoline which does not collide with any existing trampolines inside this trampoline page. So by using this same search order for page selectors, we are trying to maximize the memory utilization of trampolines of probes lying close to each other. So this scheme is general, but there are certain cases still we can improve. For example, let's say we want to instrument the exit of this malloc function, which is just a 1 byte return instruction. So if we probe here, our jump instruction will basically override the first few bytes of the free function, which is just happens to be right next to the malloc. And so this is not unsafe, but let's say we are calling this free function very frequently inside our application. So now whenever we call free, it will basically trap due to the probe that we have here. And it's quite detrimental to the performance. So for this reason, we try to avoid sort of panning across non-basic block boundaries. So the solution in this case is to backtrack in the instruction stream so that we have enough space to override our trampoline jump. So now we have to sort of ensure that we relocate all the instructions within this backtrack window to be inside the trampoline that we generate. And also we make sure that we convert all the instructions inside this backtrack window to be traps, so that so we do that because if any thread receives from these intermediate instructions within this backtrack window, it will get basically rerouted via our trampoline, so that we will not miss any calls to instrumentation after we inject this probe. So moving on to evaluation. So we came up with several micro benchmarks which determine if these probe operations, or basically attaching the probe, is reasonably low cost, and also if the trampoline memory usage is not prohibitive for a typical instrumentation use case. And we compared our solution with Dynins, which is like the state of the art for runtime instrumentation. So it also uses trampoline-based probe insertion, so the comparison is like apples to apples. So unlike our solution, it requires an out-of-process mutator, in the sense that a separate process. So it uses this, in Linux, it uses ptrace in order to connect to the running application and affect the instrumentation on the application. So when it does it, it basically stops or pauses the application and all the threads before carrying out the instrumentation. So in that sense, Dynins has this setup cost component for the instrumentation, which includes inter-process communication and the cost related to stopping all the threads before carrying out the instrumentation. So we measured this setup cost separately, and it turns out that this setup cost is significant. So it's in the order of several seconds, and here I've given the figures in megacycles. But the injection cost itself is comparable to our solution, which we call LightInst. And actually, it's a little bit cheaper than ours. We think this is due to the fact that it does not need to deal with the thread contention, because again, it stops all the threads before instrumenting, which we don't do. But the takeaway here is that with the setup cost included, our solution is on the order of several thousand times cheaper than Dynins. So that means Dynins is more suitable for bulk infrequent probe injections. And finally, we measured the trampoline memory overhead on several spec benchmark applications. So the instrumentation task here was to instrument all the function entries and exits and run the benchmarks. And we measured the trampoline overhead as a percentage of the max memory residency of each program. And the highlights are the maximum overhead that we observed across the applications was around 2.8%, and the geomin was around 0.08%, which is very reasonably low. And here's another view of that benchmark, which is these solid blue bars correspond to the max memory residency of each program. So you can see the Perl bench allocated the most amount of memory, but the maximum overhead occurs at Homer application, which is 2.8%. All figures are in kilobytes. So this brings me to the end of the presentation. So we presented a lightweight instrumentation technique using core trampolines, and we use this novel technique called instruction finding to find, say, trampoline jump offset at any instruction, and it's low overhead in terms of probe insertion and memory usage for typical instrumentation use cases. And we think it would be a very useful technique for any tools which depends on lightweight runtime binary instrumentation. Thank you.
All right, we have time for a couple of questions.
Thank you for the talk. So I was wondering about your comparison to Dynast. So by the startup cost, do you mean the one-time startup cost when you start your application, or every time you do an insertion?
You mean the setup cost?
Yeah, sure.
Every time you do an insertion.
Oh, okay, okay. So it really is an apples to apples comparison there, and it's not. So for long running applications, it would still you'd see the same effect. Okay, thank you.
Hey, quick question. How many different places can you put the trampoline page in? Because you're using specific bytes which are illegal. And you only have the 22 bits local jump to use. You can't use the whole address space.
Yeah, you cannot like use the whole 64-bit address space. Yeah, so we didn't like really measure how many like places that we can put, but like with like all the benchmarks that we did, like we didn't run into an issue where we couldn't find place to like even still like it's like 2 to 32, right? Because not 2 to 30, but like 20. But still, that's like a good enough space.
Yeah,
to
but you have the stacks. You have the stacks and the heaps for multiple threads, maybe.
I'm sorry.
You have multiple threads, maybe in the program, and then each of them has a stack and a heap.
Mm-hmm.
So you might get in a predicament when you can't place the trampoline page.
Right. So the thing is, like, one solution I can think of is like to chain trampolines so that like, so typically in our solution, the trampoline is like, I think it was like 120 bytes, including like the call setup cost and like the call setup and the teardown. But one thing I can think of is like to chain the trampolines in a way such that like, so if you don't find enough space to place the full trampoline of like, let's say 120 bytes, you just like place a jump, which would like extend the reach of this thing so that like, you can jump off to the trampoline, which can be like somewhere outside to the 20 or something. And that's one potential solution I can think of. But again, like we didn't come across this particular scenario that you said where we weren't able to, yeah.
Thank you.
Hi. It looks like there's a somewhat obvious comparison, which was not really discussed here, which is with a more traditional DBT system where all code is relocated to a code cache. In particular, in terms of insertion costs, that is generally way cheaper, maybe on the order of thousands of cycles, not millions of cycles.
I'm afraid I didn't get your question. Can you sort of repeat
so
that?
I was saying that in as opposed to this technique where you modify the code in place, you have the more traditional approach where you relocate all code to a code cache, so like a pin or Dynamo Rio. In that case, your insertion cost gets way lower than this. I was wondering if you've looked at where's the trade-off when it's better to use this sort of technique and where it's better to just relocate all code.
If I got your question correctly, the question is like, have we compared this with like techniques like dynamic binary translation, which Dynamo Rio and Pin uses? Is that right? No, we have not. But as you said, like dynamic binary translation incurs like this sort of startup cost of like this initially translating every instruction, right? So that sort of incurs like sort of a lot of non-trivial initial overhead. And also like if you want to like instrument, like if you want to like re-instrument the application, or like if you want to insert probes basically like throughout the run of the application. So in that case, basically with Dynamo Rio, for example, like you will have to invoke this binary translation again and again, and you will have to basically unlink the generated code caches and then relink them. And so I think where our solution shines is that like in use cases where like you want to like probe the application frequently. For example, like in the case of like, let's say a statistical profiler, you don't want to like keep the instrumentation on for like the entire duration of the application. So you need to like, keep it on for a bit and then turn it off and like do this periodically. So in that case, our solution really shines, I think, in comparison to Dynamo Rio. For example, in that case, because like Dynamo Rio has to like now, invalidate the code caches and do all this, like go through this whole process of like re-instrumenting or like running the interpreter, like binary transmitter again and again.
Okay, we would have time for one final question, if anyone has one. And if not, then let's thank the speaker again.
Thank you.